Um, okay, so we are live for today's session. Thank you everyone for joining and a warm welcome to all of you on behalf of Naukri Learning to today's live session that is building neural networks using TensorFlow. Thank you so much for joining us on a Friday evening, and it's a great pleasure for me. I welcome and introduce our speaker for today, Rajesh Gupta. He's currently a data scientist at Naukri.com, and he's working in the field of NLP, and he's also an alumnus of IIT Kanpur. Okay, so before we start, I would, sort of remind all of you to keep posting your questions in the live chat box so that, we will try our best to answer it. And also towards the end of the session, please stay up till the end of the session because a lot of questions may be answered towards the end as well. So without further delay, let's get started. Over to you, Rasesh.
Yeah, thanks, Niharika. Thank you everyone for joining. So today we will be talking about TensorFlow, which is a Python library and which is very useful for designing and building neural networks. So we will cover the basics of TensorFlow in this session today. So this is what we'll be covering today. So first I will be telling you about TensorFlow. What is TensorFlow? Then I'll tell you about how to build your first ML model using TensorFlow. So this will be a very simple linear regression model that can get you started on your deep learning journey. Then we will solve an image classification problem using TensorFlow. So here we will train the model using both sequential and functional APIs. So this will be sort of a transition to the functional APIs, which open up a vast array of neural networks that can be created. Then lastly, we will cover a slightly advanced multi-input Siamese network model that will tell us whether two images are similar or not, or dissimilar. So this again will be creating the model using functional APIs. So what is TensorFlow? So it's basically a Python library which was created by Google in 2015. So initially it was used by Google internally, but they open sourced it later on. Internally, it uses data flow graphs within it to as a data structure to for data flow. So using TensorFlow, we can create models using majorly using two APIs, sequential API and functional API. Sequential API are simpler to implement, but have certain limitations. Functional APIs, on the other hand, are a bit complex, but using functional APIs, we can create a lot of complex models as well. So computations in TensorFlow are done using tensors, which are basically multi-dimensional arrays. So for this session, since we'll be covering TensorFlow, so you'll be familiar with basics of deep learning. Even if you are not, I'll try to cover the basics as well. So for job seekers, like every data scientist should have implemented a few deep learning models, because my experience also says that in interviews, interviewers generally look for the projects that you had implemented using in data science, and the interviews are driven in that direction depending on the projects that you have done. So you should have done some standard problems like sentiment analysis, image classification, or maybe some advanced project like object detection or object localization. This will add a good value to your CV. So now let's move on to building your first ML model. So how do we build, what are the steps involved in building an ML model? First of all, we need data. Data we can get from any source. So in TensorFlow, there is lots of data available in TensorFlow.keras.datasets library. In short, it is called TFDS library, or we can have it locally as well. Once we have imported the data, it is very important that we clean the data for training. I think this step is quite underrated, but just this step alone, a good preparation and a good data cleaning can significantly improve your model performance. So there is no set way to how to prepare or clean data. It actually depends on the data. That how do we need to clean it. But in general, for NLP tasks, there are libraries like NLTK or Beautiful Soup that can remove stop words or parse HTML for us, which are pretty useful. In computer vision, there are majorly two things that one might need to do. The first is the normalization of the matrices that we have, image matrices that we have, and the other is data augmentation, which is a very powerful technique that can reduce overfitting. So once we have cleaned the data, now we need to set up our model hyperparameters. So they will most probably be needed to be tuned after further training, but it's good to have set that we set an initial value. So model hyperparameter, there can be many hyperparameters depending on the model. Learning rate is one such very common hyperparameter. Now, once we have set the hyperparameters, now we need to define our model architecture. It depends on the problem that we are solving. It depends on also depends on the complexity of data that we have. So it usually consists of one or more layers. So this is our focus. The model architecture is our focus for today's session. Now, once we have model architecture in place, there is a few more things that we have to configure in the model, like the loss function and the optimizer. These two, loss function and optimizer, basically train our model, and we'll see how we need to choose them. Now we can train the model and then later on evaluate it. So in TensorFlow, what are the various types of layers that we can use? So we'll see them in the later slides, but just I'm just giving a brief introduction about these layers. So one of the first is a flattened layer, which basically converts a two-dimensional input to one dimension. So in machine learning models, it is used to convert the image matrix that is in two dimensions to a single dimension, so that it can be fed later into dense layers. Dense layer is basically a layer of neurons. Here we can specify the number of activations, the activation function, and the number of units that we need to define. Another very common layer that is generally used in machine learning and deep learning is convolutional layers. Convolutional layers are a topic in themselves. So on a high level, these layers basically apply a set of filters, and they are just very powerful. They can learn very complex features. Then Maxpool layers are usually followed by convolutional layers. So the convolutional layer has learned very complex features. So what Maxpool layer does is it highlights or retains the features that are dominant and sort of removes the non-dominant features. So convolutional Maxpool layers are a topic in themselves, so we'll maybe cover them later on. Now, LSTM layers are actually very useful for textual data, because they take into account the context of the words which come before or after a particular word. Then there comes lambda layer. So using lambda layers, we can execute any arbitrary function. If you want to compute cosine similarity between the two vectors, or Euclidean distance between the two vectors as a layer, then lambda layer is the one which we should be using. The other is embedding layers. They contain the vector representations of words and vocabulary. So this layer is actually very useful, is generally used after the input layer. And once we train the model, this can give us the word embeddings of using the data. And if we don't, if we have some other thing in mind, then we can also actually design custom layers using model subclassing. We will not be covering in this session. So now, as discussed earlier, as a first ML model, we will be building a linear regression model using deep learning. So what is a linear regression problem? A linear regression problem is basically learns a linear model given data. So it assumes that the relationship between the input and output is linear, and then basically tries to derive patterns, or basically learns the data. So the model architecture is pretty simple in this case. It will always contain a dense layer. If we have multiple dense layer, basically imply a nonlinear function. So one dense layer will imply a linear function. So as discussed earlier, so let's go to the slides that we have prepared. Okay, just put a notebook. So here, this is basically, I have implemented a linear regression model here. So I'll tell you the basics and how we can create here as well. So what I have done here is, I have generated X is the input and Y is the output, and I have generated 50 data points between 0 and 10. And I have also defined the output as 1.5 times X plus some noise, small noise. So if we label this data, plot this data, then we will have some sort of a linear relationship and with some noise. So let's train a model, linear regression model on this. So now what we have is, we have to define one dense layer. So we will use sequential APIs to define a dense layer. So how we can do that? The syntax is actually quite simple. So to define a sequential model, we just have to use the Keras API and then define a dense layer. I have done it here. And here in linear regression model, since the output is always a scalar, the number of units will be 1. Input shape in our case is a single dimensional. That's why the input shape here is defined as 1. But if we have a more complex data with a lot of features, then it can be more than 1 as well. And lastly, we need to define the name of the, it is useful for debugging purposes for very complex models. So what does this step do? So this step basically, so I have mentioned earlier that internally TensorFlow uses data flow graph. So this step basically creates a graph of that network. In this case, it will just be a node, but for complex network, it will be a graph, which we'll see later on. Now, once we have defined the model architecture, the next thing we need to do is to define the optimizer and the loss function. So why are these important? So loss function basically computes the error between the model prediction and the true output. For example, so it is basically generally higher when the model error is high, and it is lower when the model error is lower. And we also need to define an optimizer. Okay. Once we have this model and optimizer and loss defined, we can train the model. Okay. So let's let me run this cell so that we can make sure that we have some data here. So I have defined the model architecture. Now we configuring the model with the optimizer and the loss function. And initially I have not trained the model. So the output should be 1.5 times x plus some noise. So uh, for any x, the output should be approximately 1 times that input. So if I try to, without training anything, if I try to predict the model, the output should have been 150, but it is very off. And on that input, if we try to plot the model, we can see that it does not really generalize. Now, what will happen? Let's train the model for one epoch. So during training, what will happen is that the loss function here we have used is the mean squared error, which is basically mean squared error basically means y the predicted error minus the predicted output minus the true output squared. Okay, and what all? So this loss function will be minimized by the optimizer. Optimizer internally uses gradient descent techniques to minimize this. We won't be covering the mathematics, but for now we can assume that this optimizer will try to minimize the loss function. So once we have trained the model for one epoch, let's check the output. So see, here we have got nearer actually to the true output, which is 150. And let's see how we are able to generalize. So here we can see that the model has learned something, but not exactly. Okay, let's train the model now on some more epochs. Let's say 10 in this case. Okay, we are getting nearer. It's 145, which is nearer to 150 to the true value, but it looks like it still hasn't trained. So let's train the model for let's say 10 more epochs, and we will get nearer and nearer. We may not be accurately able to define the output because of the noise in the data, but this is how a model learns. Okay.
Rasesh, a few people want to know what is optimizer.
Okay, sure. So an optimizer is basically okay, I have covered it in the slides. So on a high level, an optimizer is basically, so let's assume that we have the model has predicted the output for an input, and we also have the true value for that input. So there will be some loss associated with that. And the loss function is usually a very curvy function, which will have a local minima. So what the optimizer will do is, let's say the minima is here. Can you see my pointer just to confirm?
Yeah, your arrow, right?
Yeah.
Yeah.
Sure. So let's say the loss is minimum loss is here, and we are trying to reach there. But initially, the model parameters will be a bit random, and the loss we might not be here. So initially, let's say the loss we are here. Now, optimizers are usually in the format of the gradient. So what optimizer does is that it computes the gradient of the loss function at that point, and based on the gradient value, it will move in the direction where the loss is reduced, loss is minimum. So it will come basically the optimizer generally is of this format where the W is the initial value of the model weights. We will compute the derivative, which is in this case is this, and then there's one more parameter called learning rate. So we will move in the direction of optimizer will let the model parameters move in the direction where the loss is minimum using this parameter, using this formula. So here learning rate is another hyperparameter that we had mentioned earlier. So we also need to tune the learning rate sometimes. If it is very high, then here we can say that in this graph model learning parameter is quite optimal. So it is actually learning. But if it is too high, then model may not go to the minimum, but may overshoot. So maybe let's say if it's here, then it might go here, then here, and then here. So the learning, if it's too high, then the model might not be able to learn. Even if it's too low, if it might take a lot of epochs, many iterations to learn or get to the minimum loss value. Okay, so this is another hypermeter that we should be chosen. Recently, there have been some research done on it, and there are actually some optimizers that can actually adapt the learning rate based on how near they are to the loss value. So here in this example, like we can see, if you can see that if currently we are here in this graph, basically the loss is higher, the learning rate will be higher because we have a more distance to travel to the minimum value. But if we are here, let's say, then the optimizer's learning rate will automatically have a decay factor that will reduce the learning rates to make sure that we are not able to overshoot to the other side. Okay. So yeah, that's about it. Hope I'm clear. And right. And the loss function, and how should we choose a loss function? So loss function should be chosen such that it is high when the model prediction is not accurate, and should be low when model is accurate, so that model is penalized when it is making an error. So in this case, we have for linear regression models, the loss function generally used as a mean squared error. So we can see that mean squared error is defined like this. So if we can see that if the prediction and the true value are very far away, then this square will be higher and the loss will be higher. And if they are near to each other, the loss will be lower. So this way we can learn the model. A deep learning network can learn. So TensorFlow actually provides one more API where we can actually check what is the model, what is the graph that the model has. So in this case, we just have an input of size 1 and one more dense layer of size 1. So it's basically a pretty simple graph. So let's move on. One more optimizer that is generally used is Adam optimizer. It is generally it generally gives higher accuracy than other optimizers, but again, not necessary. But most you should if you are building a model for the first time, you should start with Adam optimizer. And yeah, let me tell you what are epochs as well. So epochs is basically the number of iterations that the model has to go through for to cover all the data. So one epoch means that the model calculates the loss value for every input once. So basically, in every epoch, the model will iterate through all the data points. So the number of rounds that the model has iterated over the data is basically the number of epochs. So here I had used SGD optimizer. There is one more optimizer called Adam optimizer. Then there are more optimizers like Adagrad. There are lots of optimizers actually. Okay. Sure. So let's move on. So this was the linear regression model, which was a very simple model in it, which contained only one dense layer. So let's move on to a more bigger network. So let's try and solve an image classification problem here. So first of all, what is an image classification problem? So in classification problems in general, we basically train a model to predict the class of every data input. So in this case, all the data points will have an associated class with themselves. Mathematically, it can be 0, 1, 2, or it can be any number. So here in every image will have a class associated with it from 0 to the number of classes -1. Okay, so here let's try and build this model architecture. We will, okay. So usually in classification problems, we do have, especially in image classification problems, we have a combination of CNN layers and dense layers. The number actually depends on the data size and the complexity. Okay, so for this particular models, it has 2 convolutional layers and 2 dense layers, which the total parameters are around 2.5 lakh. So let's go through the notebook. So here I have already loaded. So as I had mentioned earlier, data TFDS library, basically the TensorFlow.keras.datasets library, already provides us lots of data to explore deep learning. So here I have already loaded some Siamese dataset, which is a very standard dataset for beginners. So let's so how is the data here? So every data point here is, so here I have print one of the data points. So we can see that Siamese dataset basically contains images of clothing. So here we can see that the shape of the numbers roughly correspond to the image output as well. Okay. So this is about the dataset. And generally, these are actually pixel values, which will range from 0 to 255. Okay, so let's first explore the data. So let's first check the input of the data. What is the shape of every image? So every image is basically 28 by 28 matrix with values from 0 to 255, and we have around 60,000 images in the training set, and I think 10,000 in the test set, and this variables will contain the labels of these images. And in Siamese data set, there are 10 labels ranging from 0 to 9. So for image data sets, it is generally good practice to actually normalize the data first, so that all the pixel values are from 0 to 1. So here I have normalized the data sets by dividing it by 255. And let's try and build this model. So I'll go slow here. So first of all, we will try to build the model using sequential APIs. So first, we have a convolutional layer, then a max pool layer. Okay. And here the input is 28 by 28, the output is 26 by 26, 64, which means that there are 64 filters, and each filter is of size 3 cross 3. Again, 3 cross 3, I can explain how it has come. If there is no padding, or if there is no padding, then basically we can predict the output value by this simple formula. Well, input shape minus filters plus 1, number of filters plus 1. Okay. So this is basically a 3 cross 3 layer followed by a max pool layer. So what does a max pool 2D layer do? So it will take 4 points and only retain the maximum of those. So for example, we can have a very big matrix. Let's say 3, 4, 5, 6. Then and so on. Okay, so what a max pool layer will do is it will take 4 numbers at one and only retain the maximum of those. So this is how it retains the most dominant feature. So the output that we have here will be 5, then the maximum of this 4 will be 12, then and so on for the third and fourth layer. So here we can see that the rows has reduced by half and the columns have reduced by half as well, because for every 4 points we are just retaining the maximum of them. So hence here the output has become half. Again, we have used a convolutional 2D layer here. Here again we have used 64 filters, and each filter is of size 3 cross 3. Then again a maximum layer which reduces the dimensions of by half, and then we have used the flattened layer which will which will make this sort of three-dimensional input to one dimension so that we can fit this network into dense layers. Okay, so this is how we can define the model using sequential APIs. So what we have to do is uh, the sequential APIs is provided in Keras tf.keras.models library. So this is basically a list of layers. That's all. So here we can stack the layers one by one. So here we have first convolutional layer, then maximal layer. So here we have defined 64 filters of each of size 3 cross 3. And in the first layer of a sequential API, we always need to define the input shape. So here, since the images are 28 by 28 by 1, we have to give the model the input shape. And then the activation which we have used is ReLU. So ReLU activation is pretty simple actually. It will remove it will basically, if x is greater than 0, then it will simply remain x, but if x is less than 0, then it will be 0. So this is another this is actually the most very popular ReLU function, and in standard as a standard, it is the most in the most used activation function. Okay, now once we have the flattened layers, then we have defined and here the max pool. Let's go on to the max pool layer. So here we have defined it of size 2 by 2, which means that for every 2 rows and 2 columns, it will give one output. In this case, max pool layer will take the maximum. There are other options as well, like average pooling, which will average those 4 numbers and so on. This again is another experimentation that which layer gives the best results. Now our output is basically a dense layer. So here, since we have 10 classes, so the dense output layer will have 10 neurons. So this number actually gives us the number of neurons. And for classification problems, in this case the multi-classification problem, the standard activation function used is softmax. So a softmax is basically a probability of the input being associated to that output. For example, let's say let's consider an output which will be of size 10. So maybe, so what will softmax does is, let's take a simple example. I hope it's 10. So the model output will be sort of this form, where the sum of all the 10 dense layers will be 1, and this is basically assigns a probability to each class being associated with that input. For example, in this example, there is a 10% chance, according to the model, that this input belongs to class 0. Again 10%, and there is a 20% chance that this output belongs to class 9. So it will take the maximum of these values and assign the class here. So in this case, the model output is that input will have class 9. Okay, so again, defining the optimizers and the loss function. So for image classification problems, the loss function generally used is sparse categorical cross entropy. And optimizer that I mentioned earlier used here is Adam optimizer, which adjusts the learning rate according to how near it is to the minimum loss function. Okay, so let me run this cells and train the data for 5 iterations. I hope it will work. Okay, so maybe the data I have disconnected here. Let me check. Okay, sorry for the slip up, but we'll work with the functional API. This was actually the model output. Now we can evaluate the model using evaluation on the test images, which can give us the loss as well as the accuracy of the model. Okay, so let's move on to the functional APIs now. So if how to write a network using functional API. So a functional API always contains three parts. The first is we have to specify the input layer. Then we have a deep network within it, and then we have to define the model based on the inputs and outputs. So let's see how we can define this model using a functional API. So in a functional API, as mentioned here, we have to first define the input layer. So this is provided in tf.keras.input. So here we have to give the shape and an optional name that we can give. Now we have to stack the layers one by one, and the syntax here is that we first define the new layer and then specify which layer it is connected to. Okay, for example, here we want that there is a convolutional layer. There's first an input layer and it is connected to a convolutional layer. So here we have defined the same convolutional layer with the same number of filters, same activation function. We have given it the input shape, and we have told the model that this is the previous layer through another bracket. Similarly, after the convolutional layer, we have max pooling layer. So again, we define a max pool 2D layer with the number of strides and specify its input to be first convolutional layer. Now, this first max pool layer will be fed into the second convolutional layer, and then the second convolutional layer will be fed into the second max pool layer. Then, okay, then this second max pool layer will be fed into the flattened layer, and then so on. We can go to the output layer. So once we have defined the model graph, we have to define the model. So this part only defines the graph, that which layers are connected to which layer. We have to define the graph. So here we have to specify the inputs to the model and the outputs to the model. So here our input is the input layer of shape 28 to 28.1, and the output here is the output layer. Here we have only one input and one output. So one good thing about this model is that we can connect any layer with any layer. If I wanted, instead of, I could have like fed this flattened layer, I could have I could have connected input layer with the flattened layer as well, and maybe have a very complex model with multiple inputs and outputs. Which we'll see later on. So so this is how model works. I hope this works now. Yeah. So this is the architecture that we have. So now this has given us the model. This will, so, okay. So there's another useful API called model.summary, which can give us the details about the layers. So here we can see the number of parameters that this model is learning. Okay, so in total it has 2.5 lakh parameters. And how did we come up with this number? Let's see. So here we have used 64 filters of size 3 cross 3. So every filter is of size 3 cross 3, and there are 64 such filters, and plus one constant for each filter is also there. Okay, then this will be added to, okay, so this will be around 64 into 10, 640, right? Now here we have another convolutional layer of 64 filters of size 3 cross 3 again, but this is now fed into a 3D matrix. Here it was just a 2D matrix. Now the matrix is actually 3D matrix. So there are 64 filters of size 3 cross 3 that are being fed into a matrix of 3 cross 64 size matrix, and again in a constant for every filter. So this is the number of, this should give 36,928 size of the matrix into the number of filters, basically. Sorry, number of filters into the third dimension into the number of filters. Again, here the number of filter size into the third dimension here was 1, so it was just 1, and then the number of filters in the new convolution layer plus the constant. Here, now here we had a layer of size 1600, and it was being reduced to a layer of size 128. So every layer in the every node in the flattened layer will be connected to every node in the dense layer. So this will give us, this will be around this. Basically, every node in the flattened layer is connected to every node in the dense layer, plus a constant parameter for each node in the dense layer. Now again, 128 nodes are connected to all the 10 nodes, plus plus a constant for every node. So this should give us 243,000. Okay. So let's train the model now. For 5 epochs, it did not work earlier, but okay, now I hope it works. So here, this might take a bit of time to load, but here we will see that with every with time, the loss will be reducing and the accuracy will get higher. And later on, we can evaluate the model to check the accuracy and the loss value after the model. So one of the questions that has come is, how did I decide the number of neurons or the dense layer? So to answer this question, this is just in hyper model architecture is also is also a parameter. So there is no fixed way that this model architecture will give the optimum output. We have to tune hyper parameters, analyze the output, analyze for which inputs the output is giving a wrong value, try to find a reason for that, and maybe if the model is not able to learn using this many parameters, then maybe we need to maybe increase the number of parameters, which might give us a hint key that the number of layers need to increase. Or maybe if it is overfitting, then maybe we need to decrease the number of layers. So this is just an this just depends on the data, that how many layers to use and which layers to use as well. So there is no set guideline for this. So so yeah, this will learn, and let's move on because this will take a while to learn. Okay, so here we have seen that to conclude, here we have seen that how we can write the same model as a functional API. So in functional, just to reminder that in functional APIs, we have to specify the previous layer to the new layer as well. Okay. And later on, we have to define the model. So this was about the functional image classification problem using both sequential and functional APIs. Now, let's compare the sequential API and functional API. So what we did in sequential, what did we do in sequential API? We just stacked the layers one by one. So it has some disadvantage, that it does not offer any flexibility, because every so let's say we want to build some complex model that can have multiple input or multiple output, or maybe a shared layer between multiple inputs. It is very difficult to implement that using sequential API. On the other hand, functional API actually offers much more flexibility. We can connect any layer to any other layer. We just have to specify the input for that layer. And there is one more actually way to build models. So for those familiar with OOPS concepts, there is one more concept called model subclassing in TensorFlow. It offers even more flexibility than functional APIs. This is a bit advanced. I think you will be able to implement most of your architectures using functional APIs itself. So let's move on to another network. In this case, we will be building a multi-input Siamese network. Okay, so what is a Siamese network? So, a Siamese network is basically a network that consists of multiple inputs both these inputs are fed into the same model. So basically these two inputs will be sharing the same parameters. And then for each of these inputs, we will be getting an output. So this model is very useful to predict the similarity of between the inputs. So here in this case, if you can see, we will for the left input layer, we are getting a vector of size 128. For the right input, we will be getting a vector of size 128, and we will compare the similarity between vectors to give us a scalar number. So again, let's go and implement a Siamese network here. So I'll move slow here because of make it easier for those who are new. So here we are again using the same data, which is of size 28 cross 28 images, and each image will have its class from 0 to 9, a total of 10 classes. So what do we have right now? We basically have an image and an associated label for every image. But here our problem is that we want to given two images, we want to identify which, if the images are similar or dissimilar, basically belong to the same class or a different class. So we have to do some data cleaning and preparation here so that the input can be fed into the model. So what does our network expect? It basically expects two inputs, basically two images, and as an output it gives us whether the images are similar or not. So our input will be two images, and our output will be 1 if the images are similar, otherwise 0. Okay. So we need to, what do we need to, how do we need to prepare our data? So we will create an array, or basically list of pairs. So here we will have I1, image 2, and maybe here image 3, any pairs, image 2, image 3, or maybe image later on image 1, image 3. And this is the input to the network, and output will again be a list which will tell us whether the images are similar or not. So here if I1 and I2 are similar, let's say the output will be 1. Then if I2, I3 are not similar, then it will be 0. Then if I1, I3 are not similar, then it will be again 0. So it will be again a list of the labels. So this is our input to the network, and we have to create our input in this way. Okay. So here there are already some functions written, and that will create the pairs. So the focus for the session is a model architecture, so we won't go much into how did we create the pairs functions here. So this function can help us in visualizing the image. So what we have done is we have again normalized the image, and we have created the pairs for image. So here the tr underscore pairs will be our vector of list of pairs of images, and tr underscore y will tell us whether if the image is similar or not. So we have around we had 60,000 training images and 10,000 test images. So we have generated around 1.2 lakh pairs for training and around 20,000 pairs for testing. So now we have the input for the model. Okay, and let's visualize some of the images using the using these our utility function. So here in this case, the images are actually different. The label is for them is 0. If we maybe switch to another image, let's see. So here both are t-shirts. So the label for them is 1. So in this way, we have around 1.2 lakh pairs for testing. And so what was our target? Our target was to build a model, another model itself, and that model will have 2 inputs followed by an output. So let's try and build the base model first. So what this here we will just follow a simple architecture for our base model, where we have just a flattened layer, dense layer, dropout, and another dense. So here we have so again, this is a model in itself, and this model will have this model will be surrounded by, will be enclosed in another model. So this model in itself will require an input layer, because here we are using functional APIs here. So here we have given the input as 28 by 28. The flattened layer will basically convert the input to 1D. So the number of neurons output it will give us 724, which is 20 times 28. Now this 728 neurons will be connected to the dense layer of 128 neurons, and then a dropout layer. So, and then a dense layer again of size 128 by 128. So this will be our output vector for each image. And again, we have to define the model. So the inputs will be the input, and the outputs will be X. Here we have encountered another new layer, which is a dropout. So dropout is basically a layer used to prevent overfitting the model. As the name suggests, point one here means that all of this 120 nodes will be connected to all the 128 nodes. So at every iteration, 10% of them will be dropped. This is what it means. If I make it 0.2, then the number of connections here are 128 times 128, and 20% of them will be dropped. And this is a dropout. In my experience, a dropout is actually a very powerful technique to prevent, very good technique to prevent overfitting. So once we have the base model ready, let's move on to the overall model that we have. So our base model is stored in the vector base network. So what do you think it should be doing? Well, I think what it should be doing is that we should be doing some base network and feed it an input 1. This will be our output 1. And there should be another input that should have the same base, that should be fed into the same base network. Okay. So these vectors, as per our model, will have the size 128 by 128, and we have to define those inputs as well. So input 1 will be input of shape 28 by 28 by 1, or we can do this one as well. And in input 2 will be similarly, we can define the input 2. Right. Now we need to, as per our architecture, we need to output a scalar given this two 128 by 128 vectors. So here we will be using a lambda layer. So a lambda layer, as discussed earlier, can be used to execute any arbitrary expression. So in this case, we are implementing Euclidean distance here. Okay. So this is actually the syntax for a lambda layer. So we have actually defined how to compute the Euclidean distance for given two vectors. So this is a syntax for the lambda layer. So what it will take is, it will compute the Euclidean distance. We have provided a functional optional name, and then we have given it an output shape. The output shape here we have given it another function, and it's actually scalar because the distance is just one scalar. And here the input, since this layer is actually taking here this model, since this model is giving us actually two vectors, so both of these vectors need to be fed. And the syntax for this is that they should be fed as a list, similar to what we should be fed as a list. So we have this output layer now. Now let's define the model. So here you can see that in earlier models we just had one variable here because there was only one input. Now we have two inputs denoted by input A and input B, and both are fed into the base network so that the parameters are shared. So we have two inputs and the output is our Euclidean distance. So let's run this model. We have got this architecture. Now, once we, so here as discussed, that once we have the model architecture, we need to define the training configuration like loss function and optimizer. Okay, so for Siamese networks, the standard loss function used is contrastive loss. So contrastive loss, I'll tell you what it is. That when the predicted output and the true output are same, the loss will be 0. So in our case, with our output is a Euclidean distance between greater than 0. Okay, so when our predicted distance and the true distance are equal, 1 1 and 0 0 in this case, the loss value will be 0. And if they are different, they are very far away, the loss value will be high. Okay, so contrastive loss basically what it will do is that we have two vectors, okay, and it has given some distance for these. So if let's say our model has predicted that these two images are similar and their distance is 0. Okay, our model has predicted that our distance is 0, while let's take one case when the true output is also 0. So in our case, the loss will already be 0 and the model will do nothing. But if the true output is 1, so the model will try to make the vectors of these two images farther away from each other. So for every two similar images that the model encounters, their vectors will be the model will try to make their vectors as near to each other, and if there are two dissimilar images, the model will try to take their vectors as farther as it can. So it is important for us that the loss function also expresses that. So in our case, for nearer vectors, we are having lower loss value, and for farther dissimilar images, we are having a higher loss value. Okay, so this is our contrast loss function. So basically this does the same thing actually. If the okay, so if y true is 1, then we just take the square of the output. So if we try to debug it, we can see that actually if y true is 1, then the loss will be the square of the prediction, and if the square of the prediction is also 1, then the loss will be 0. Okay, so now let's try and compute it on some epoch. So here we can see that the loss is actually reducing bit by bit, and once we are able to, so we have actually very loss value initially, but it will actually improve with the number of epochs. Okay, so once it will take a bit of time to load, but let's move on. So here we have used an RMS prop optimizer, which is another optimizer. Again, I think the Adam optimizer will again work better here. So let's move on to another network, which is a multi-output network. Here there is only one input and it has multiple outputs. So the practical applications of such a network involve object localization, object segmentation. So generally in object, in these kind of problems, one of the output gives us the category of the object, what category the object belongs to. For example, object localization is a very common problem in auto drive or driverless vehicles. So okay, so every vehicle will, for at every moment that driverless vehicle will be like, we can consider that it will be running this model. One of the output it will get is the category of that object it is seeing. Maybe it can be a building or it can be a tree or anything like that. And the second output generally gives the location of that object. And it is generally implemented as a linear regression problem. So object segmentation and localization is basically combination of classification and linear model. This will give the category of the object and the other output will give the location of the object. And let's again build this architecture. Here I don't have any data, so let's just focus on building the architecture. So let's just focus on, so our target is this layer. So here we can see that this layer should be fed into two parts, two different layers. So as always, we have an input layer of a certain shape, then a first dense layer, which first dense layer for which the input is the input layer, then a second dense layer which is connected to the first dense. Now this second dense layer, once we have this, we will have another dense layer and another output layer. So we have the first output layer, and this output layer is connected to the second dense layer, and then another third dense layer, which is connected to the second dense layer. So this way we are able to get this sort of a graph. And then again, subsequently, this third dense will be fed into the output, another output, and giving us the model. So here in the Siamese network, we had a list of inputs. Here we have a list of outputs. And if the inputs and outputs both are multiple in the model, then it can also be provided as a list. Okay. So this is our model. And okay, let's cover this as well. So since there are two outputs in the model will try to we need to specify the loss function for both the outputs as well as the optimizer for both the outputs. So here we can do this using this syntax. So basically the loss that we defined actually earlier in image classification, we had defined it as a string. The optimizer was also a variable, but we can actually define it as a dictionary. So here the name of the layer, which is optional initially, comes to play. So we can specify using the name of the layer that which output layer will have, which will be evaluated using which loss function. So in our case, the y1 output, this layer will have mean squared error loss function, and this output will also have a mean squared error. But it can be anything, like we can make it a sparse, categorical, cross entropy, anything. Both of them are independent. And the optimizer for them, here we have kept both same for both. So this is about a basic multi-output model. So here keep in mind that this we are partitioning the models. So the one layer will be fed into two other layers, right? So let's move on. So these are actually the basic building blocks of building a network in TensorFlow. So what are the next steps for you? The first, go and explore the world of deep learning. Train a few models yourself. I suggest that you try, if you're new into machine learning or do not have any experience in machine learning, or try some standard problems like sentiment analysis or image classification. And then you can, and then later on you can go for very complex models like object detection or localization. And model subclassing is something which we did not cover. You can also get familiar with it. It can actually make our life much simpler when we are trying to build very, very complex models. There is one more concept in TensorFlow called data generators. Actually, this is a very helpful technique that can save us RAM. We do not need to load all the data into RAM once. What data generators do is that it will take load a batch of data into RAM, process it, then free it from the RAM, then load another batch of data into the RAM and process it, and then free the RAM, and so on. So this can save us our infrastructure. Then there is one more technique in machine learning called transfer learning. you can go and read about it, and of course you can go and participate in various data science competitions to get familiar with how to train a model. Thank you, and we can go into questions. So are there any questions, Niharika?
I think we've pretty much answered the question. I don't think there's any new question as such.
Okay, sure.
Yeah. Thank you so much, Rakesh, for a really nice session. It was quite good, and the hands-on exercises, I think that must have proved to be quite helpful.
Thank you, Niharika.